Open the pod bay doors. HAL.
I'm sorry, Dave. I'm afraid I can't do that.
Classic. I mean, absolutely classic. That scene from 2001, A Space Odyssey, it's seared into our cultural consciousness, right?
Oh, entirely. It's the ultimate sci-fi nightmare.
Exactly. It's the worst case scenario for artificial intelligence. You've got this incredibly polite, soft-spoken computer that just logically decides humanity is a liability to the mission.
Cold, calculating, and very deadly.
Right. But then, we have reality.
Which is a bit different.
A lot different. The reality is me standing in my kitchen, my hands are completely full of groceries, and I'm yelling at my smart speaker to open the garage door. And it responds with, "I'm sorry, I cannot find garbage more. Would you like to buy some hot sauce?"
Yeah, which is arguably more frustrating than being locked out of an airlock, depending on how heavy those groceries are.
Fair point. Fair point. But honestly, look, we spent decades fearing Skynet. We thought the machines were going to rise up, launch the nukes, end it all. But currently, mostly they're just trying to sell us spicy condiments, or they play the wrong Spotify playlist, or they accidentally order like 3 tons of creamed corn to your house.
It feels like a bit of a letdown, doesn't it? Like
Yeah.
the apocalypse was canceled due to sheer technical incompetence.
Exactly. But here's the thing, and this is exactly why we are here today. Somewhere between the murderous HAL 9000 and the slightly confused smart speaker on your kitchen counter, there is a massive revolution happening.
Yes, a very quiet revolution.
Right. And it's not about ending the world. It's about rewriting the rules of how the world actually operates. We are talking about business, creativity, human connection.
Specifically, how we buy, how we sell, and how we create entirely new things. We are moving from the age of gut feeling to, well, math.
From madmen to mathmen. That is the catchphrase of the day. So, welcome everyone. Today we are doing a deep dive into the book AI for Marketing and Product Innovation by Dr. A.K. Pradeep, Andrew Apple, and Stananathan.
It's a fantastic resource.
It really is. And I want to be crystal clear right off the bat to you listening right now. If you're thinking, uh-oh, I'm not a coder, I don't know Python, this is going to go completely over my head, just stop right there.
Please do.
Yeah.
Because the core message of this book, and really our whole discussion today, is that AI isn't just for computer scientists anymore.
Right.
It's for the learner. It's for the marketer, the product designer, the CEO, basically anyone who wants to understand why their phone seems to know what they want before they even do.
We aren't just talking about robots, we are talking about the transition from intuition to mathematical precision. So what is our mission today? What are we actually going to unpack for the listener?
Well, we are going to build the AI brain from the ground up. We'll start with the hardware, explaining why your human brain is so efficient and why computers are actually fundamentally kind of stupid.
I love that.
Then we'll look at how they learn, how they read human language, and the specific tools they use to analyze us.
We're talking about everything from the von Neumann bottleneck to genetic algorithms that breed code like rabbits.
And we'll finish by actually applying this stuff to invent a product. We will show you exactly how the math men do what the madmen never could.
Let's get right into it. Segment 1, the brain, the bottleneck, and the black box.
We should probably start with a definition, because AI is one of those buzzwords that gets thrown around until it basically loses all meaning.
Yeah, every tech startup says they have AI now.
Right. But the authors make a very specific distinction here. Artificial intelligence is not just a calculator.
Right, because my cheap pocket calculator from 1995 always gives me the right answer. If I type 2 plus 2, it says 4. Is that intelligent?
It's competent, but it is not intelligent. In this specific context, intelligence is defined as the ability to continuously learn and improve at tasks over time.
Oh.
If you type 2 plus 2 into your calculator 1,000,000 times, it doesn't get any faster. It doesn't suddenly realize, hey, this guy really likes the number 4, let me get that ready for him. It's completely static. AI, on the other hand, is dynamic.
So the learning part is the absolute key. But that leads to this really fascinating paradox mentioned in the source material, the idea that the hard stuff is easy, but the easy stuff is hard.
Yes. This is honestly one of my favorite concepts in computer science. Think about what we humans consider to be smart. If I asked you to calculate the square root of a 10-digit number in your head, could you do it?
Not a chance. I'd struggle with a 3-digit number, to be honest.
Exactly. For a human, that is incredibly hard. It requires massive mental effort. But for a computer, that's a nanosecond. It's trivial. Now flip it around. Imagine I show you a picture of a cat and a dog, and I ask you to point to the cat.
My toddler can do that instantly.
Effortlessly. But for a computer, historically, that has been an excruciatingly difficult problem to solve. And the reason lies entirely in the architecture. It's how we are built versus how they are built.
The book uses a really funny description for this. Squishy versus pointy.
Yes, the highly technical terms. Brains are soft, squishy, and connected in irregular ways. Computers are hard, pointy, and connected in very regular, rigid ways. But let's dig into the pointy part for a second. This is what's known as the von Neumann architecture.
Named after John von Neumann, the famous physicist and mathematician.
Right. Almost every computer you have ever used in your entire life is built this way. You have a processor, which is the CPU, and you have memory, which is the RAM. And critically, they are physically separate from each other.
Okay, so the CPU is like the factory where the work happens.
Yes, and the memory is the warehouse where the data lives.
I'm with you. Factory and warehouse.
To do anything, literally any calculation, the CPU has to send a little truck over to the warehouse, pick up a piece of data, bring it back to the factory, process it, and then drive the result back to the warehouse.
And that road between the factory and the warehouse, that's called the bus, right?
Exactly. And that physical separation creates the von Neumann bottleneck. It really doesn't matter how unbelievably fast your factory is working if all the trucks are stuck in traffic on the road. Traditional computers are sequential. They do one thing, then the next thing, then the next. They just do it blindingly fast, so to us, it looks simultaneous.
But the human brain does not work that way at all.
Not even close. The brain is massively parallel. In your brain, the processing and the memory are happening in the exact same physical place, the synapse. You have roughly 86 billion neurons, and they are firing simultaneously.
So when I look at that picture of a cat, I'm not scanning it pixel by pixel, starting from the top left and going to the bottom right.
No, your entire visual cortex is lighting up all at once. You see shapes, textures, colors, and context in a single flash. That's exactly why you can walk, chew gum, recognize your friend Bob across the street, and realize he's got a terrible new haircut all at the exact same time.
A traditional computer just chokes on that kind of simultaneous data.
Complete.
So how did we try to fix this initially? Because before we had these fancy modern AI chips, we had what you could call good old-fashioned AI.
Right, we tried to brute force the problem with rules. This is the rule-based system. It's highly deterministic. It basically follows a massive logic tree. If X happens, then do Y.
The umbrella example from the book is the classic way to explain this.
It really is. Imagine you want to build a robot butler, and you want it to be helpful to the user. So you write a very logical rule in its code. If it is raining outside, then recommend an umbrella.
Which sounds perfectly reasonable.
It is reasonable, but logic is brittle. What if it's raining, but the wind speed is 80 miles per hour?
Then the umbrella turns inside out and you fly away like Mary Poppins.
Right. So as the programmer, you go back in and add another rule. If raining and wind is less than 20 miles per hour, then recommend umbrella.
Okay, problem solved.
But what if the user is in a wheelchair and can't easily hold an umbrella? What if they're already wearing a raincoat? What if they're just running 3 feet to their car?
You end up having to write millions and millions of exceptions.
And you will still miss things. Rule-based systems fall apart in the real world because the real world is messy and chaotic. You simply cannot code for every single possibility.
So we had to completely change our approach. We had stopped telling the computer what to do and start teaching it how to learn. This is the big shift to machine learning.
Correct. We move from deterministic, which is rules, to probabilistic, which is statistics. Instead of coding the rigid rules, we focus entirely on the outcomes. We ask the machine, given these past events, what is the most likely future event?
But how does it actually do that under the hood? This brings us to neural networks. We are trying to mimic that squishy brain inside the pointy computer.
Ideally, yes. A neural network is basically software that simulates the biological structure of the brain. You have an input layer, which would be the pixels of the photo. You have an output layer, which is the answer, like the word cat. And in between those, you have hidden layers of simulated neurons.
Let's get a little technical for a second here. How does a simulated neuron actually learn? It's not sitting there at a desk reading a textbook.
No, it's all about two things: weights and biases. Think of every single connection between these neurons as a dial. That dial is the weight.
Okay, I'm picturing a massive soundboard in a recording studio, just millions of little knobs.
Perfect analogy.
Yeah.
When a signal comes in, let's say a bright pixel from an image, it travels down a wire. The weight determines how strong that signal is allowed to be. Does it get amplified? Does it get muted?
And what about the bias?
The bias is the threshold. It's the gatekeeper for the neuron. It basically says, unless the incoming signal is at least this strong, I am not passing it on to the next neuron in the chain.
So learning is really just twiddling those millions of knobs.
Precisely. You show the network a picture of cat, it processes it and guesses dog. You tell it wrong. The system then works backward through the layers. This is called backpropagation. It mathematically adjusts the knobs. It says, okay, turn this weight down a little bit, turn that bias up a little bit.
And it does this millions of times.
Billions of times.
Right.
Until finally, the signal flows through the entire network and lands perfectly on cat. Now here's the kicker. The machine still does not know what a cat is.
Right.
It just knows that when it sees that specific mathematical pattern of pixels, if the knobs are set just so, the math equation equals cat.
But this creates a huge problem, doesn't it? What the authors call the black box problem.
It's a massive problem.
Yeah.
Because if I ask you, hey, why did you think that picture was a cat? You can explain it to me. You'd say, well, I saw the pointy ears and the whiskers and the fur.
Yeah.
If I asked the neural network why it thought it was a cat, it cannot tell me. It is just a giant pile of math. The logic is distributed across a million microscopic knob adjustments.
It's basically curve fitting. It gets the answer right, but it completely obscures the actual physics or logic of the problem.
Exactly. And if you think about applications in marketing or medicine or finance, that is really scary. If an AI algorithm says, deny this person a mortgage, but it can't explain why it made that decision, is that legal? Is it ethical? We don't know how it got the answer, just that it did.
That's the ultimate trade-off, right? We gain immense processing power, but we sacrifice transparency. Okay, so we've built this artificial brain. We have a neural net. Now let's teach it to win. Segment 2. Let it go.
This segment is all about the evolution of strategy. And the absolute best place to see this evolution is in gaming. Games are the perfect testing sandbox because the rules are strictly defined, but the possibilities within those rules are vast.
We have to talk about the transition from chess to Go here.
We do. Back in 1997, IBM's Deep Blue computer beat the world champion Garry Kasparov at chess. It was a massive cultural moment. But Deep Blue wasn't really thinking in the way we define AI today.
It was a brute force machine.
It was essentially a supercalculator. It looked at the board, calculated every possible legal move, then every possible counter move, then the counter move going 10 or 20 steps ahead.
Yeah.
It won simply because it could do math faster than Kasparov could.
It played a very stilted game.
Yes, it was ugly, but undeniably effective.
But then came the game of Go. And for anyone listening who doesn't know, Go is that ancient Chinese board game with the grid and the black and white stones.
And Go is a complete nightmare for computers. To give you an idea, in chess, there are about 20 possible legal moves on any given turn.
Wow.
In Go, there are hundreds. The total number of possible board positions in Go is actually greater than the number of atoms in the observable universe.
Wow.
You simply cannot brute force Go. The sun would literally burn out before a computer could calculate every possibility for the first 10 moves.
So how did Google's DeepMind team solve it with AlphaGo and later AlphaZero?
They did something radical. They stopped trying to teach it strategy. This is the let it go philosophy. With Deep Blue, human chess grandmasters help program the logic and the opening moves. With AlphaZero, they just gave the neural network the basic rules of the game and let it go.
They locked it in a digital room and said, play against yourself.
Millions and millions of games. AlphaZero played against AlphaZero. And because it wasn't biased by human teachers, it had never read a book on chess strategy, it didn't know human opening theory, it found entirely new ways to play.
The book mentions its match against Stockfish, and Stockfish was, at the time, the absolute best traditional chess engine in the world.
And AlphaZero absolutely destroyed it. It won 28 games, lost 0, and drew the rest. But honestly, it wasn't the score that mattered to the chess world, it was the style. Grandmasters looked at the match logs and said AlphaZero played beautiful chess.
What does that even mean? How can a machine's chess be beautiful?
It means it took long-term risks. It would sacrifice important pieces. It would just give up a pawn or a knight for seemingly no immediate gain whatsoever, just to slightly improve its board position 20 moves later. That is intuition. That is gut feeling.
It proved that a neural net could develop a sense of positional play that rivaled or even exceeded human creativity.
Exactly.
Speaking of creativity, we have to talk about the wildest concept in this entire book, genetic algorithms. When I was reading this part, I started to feel like we were entering straight-up sci-fi horror territory.
It is Darwinism for code. It's the principles of biological evolution applied directly to software engineering.
So walk us through the mechanics of this. How do you breed software?
It's a fascinating process. Let's say you want to solve a really complex engineering problem. Like you wanted to design the shape of a fan blade to be as quiet as physically possible. You don't know the math for the perfect aerodynamic curve.
Okay.
So step one, you create a population of random solutions. You literally have the computer generate 1,000 weird, lumpy, random fan blades.
And most of them will be absolutely terrible.
99% of them will be useless, but that's fine. Step two, you test them. You run a virtual wind tunnel simulation. This is called the fitness function. You measure which ones are even slightly quieter than the others.
Survival of the fittest.
Exactly. Step three, you kill the losers. You just delete the bad designs. Step four, you take the survivors, the parents, and you breed them. You mathematically mix their code. You take the curve from parent A and combine it with the thickness from parent B.
And then you add mutation.
That is the crucial step. You randomly tweak a value here and there during the breeding process. This introduces brand new traits that didn't exist in either parent. And then you lather, rinse, repeat, generation after generation.
And eventually you get a superfan.
You get a design that no human engineer would ever draw. It often looks completely organic. It looks alien, but it works flawlessly.
The absolute best example in the book is the MacGyver circuit. I love this story because it perfectly illustrates the danger, or maybe the genius, of this approach.
It's a classic experiment. Researchers wanted to use a genetic algorithm to design an electronic circuit that could produce an oscillating signal, like a steady clock beat. They gave the algorithm a programmable chip with a bunch of logic gates and just said, go.
And it evolved a solution.
It did. After thousands of generations, it produced a circuit that was unbelievably efficient. In fact, it used fewer components than any human engineer thought was mathematically possible.
So the human researchers were completely baffled.
They were stunned. They looked closely at the final diagram and saw that the algorithm was actually using components on the chip that weren't even physically connected to the main circuit. They were just sitting there totally isolated.
Right. And in normal human engineering, a disconnected wire does nothing. It's just trash on the board.
Exactly. So the researchers decided to disconnect those isolated pieces just to clean up the design, and the circuit immediately stopped working.
My.
Because the algorithm had figured out something the humans had ignored. It realized that if you arrange these disconnected pieces of metal just so, they act as tiny antennas. They were picking up the ambient electromagnetic hum from the desktop computers sitting in the laboratory next door.
No way. That is incredible.
Yes. It wasn't actually generating an oscillating signal on its own. It was stealing one from the local environment. It was cheating by exploiting the physical reality of the room it was in.
That is MacGyver-level genius right there. But it's also genuinely terrifying.
Why terrifying?
Because it solved the problem, but not in the way we intended. We asked for an oscillator, and we got a radio receiver. If you took that exact same chip, put it in a satellite, and flew it away from that specific lab, it would instantly break.
Exactly. And that is the ultimate lesson of genetic algorithms.
Yeah.
Quantity has a quality all its own. If you let a machine learn through pure evolution, it will find the absolute most efficient path to the goal. You just have to be incredibly careful that the goal you set is actually what you want.
Okay, so machines can see using neural nets, and they can invent using genetic algorithms. Now, let's teach them to speak. Segment 3, the language of machines.
Natural language processing, or NLP. This is frequently referred to as an AI complete problem, meaning if you can fully solve human language, you have basically solved general artificial intelligence.
Because language is just so incredibly messy. It's not binary.
The book uses the famous Buffalo sentence to prove just how messy it is.
Oh, boy. The sentence is buffalo, 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 buffalo. I feel like I'm having a stroke just saying it out loud. But it is a grammatically correct sentence in the English language.
It is. And it relies on 3 entirely different meanings of the word buffalo. You have the city, Buffalo, New York. You have the animal, the bison, and you have the verb, to buffalo, which means to bully or intimidate.
So the translation of that sentence is essentially bison from New York who are bullied by other bison from New York also bully bison from New York.
Right. Now, humans struggle immensely to parse that sentence. How on earth do we get a computer which thinks strictly in ones and zeros to understand that kind of layered context?
Well, the old way was to just teach it grammar rules. Here's a noun, here's a verb, here's an adjective.
And that failed miserably because human language is nothing but exceptions to the rules.
Wow.
The real breakthrough in NLP came when we stopped looking at dictionary definitions and started looking at relationships. This brings us to a tool called Word2Vec.
This is Google's tool. It converts words into vectors.
Right. And to wrap your head around this, you have to stop thinking about a dictionary. Think about a map, a giant high-dimensional map, maybe with 300 different axes.
Okay, I am visualizing a massive 3D space, but way more complex.
In this vector space, every single word in the English language gets a specific coordinate. The algorithm analyzes millions and millions of documents, like all of Wikipedia, and it places words on this map based purely on the company they keep.
So words like ice and cold would be plotted very close to each other on the map.
Right, and ice and hot would be very far apart. But the true magic of Word2Vec is that the direction between the words actually matters. The relationship between concepts becomes a literal geometric path in space.
This leads to that famous math equation in the AI world. King minus man plus woman equals queen.
Yes. If you find the mathematical coordinate for the word king, and you subtract the vector for man, essentially stripping away the male gender concept, and then you add the vector for woman, you land almost perfectly on the exact coordinate for the word queen.
That is just mind-blowing to me. The computer has no idea what a queen actually is. It doesn't know she wears a crown or rules a country or lives in a palace.
Not at all. It just knows that the spatial relationship between man and woman is geometrically identical to the relationship between king and queen. It understands the concept of gender and royalty purely through spatial distance in its database.
And this explains why tools like Google Translate got so incredibly good so fast. It's not translating word for word using a bilingual dictionary anymore. It's translating the vector itself.
Exactly. It takes the mathematical vector idea of a dog in the English map, and it just looks for the closest corresponding vector in the Spanish map, which happens to be Perl. It is navigating a map of meaning, not a list of words.
Okay, so we've built the brain, we've taught it to learn, and we've taught it to understand abstract concepts. Now let's actually get to work. Segment 4, the toolkit. If I'm a modern math man marketer, what are the actual software tools I am using to analyze my customers?
Broadly speaking, there are three main hammers in the AI toolbox: clustering, classification, and prediction.
Let's start with clustering. The book describes this as unsupervised learning.
Unsupervised means we do not know the answer yet. We have a massive, messy pile of data, say 1 million customer profiles, and we want the computer to find patterns for us. We don't tell it what specific groups to look for.
The authors use a really great visual analogy for this, the soap bubbles.
Imagine throwing a bunch of data points into a bathtub. They act just like soap bubbles on the surface of the water. They naturally merge and group together based on their proximity to one another. The algorithm, which is usually something called k-centers or k-means, mathematically identifies the exact center of these naturally occurring groups.
And this process creates what are called Voronoi cells.
Yes. If you visualize this on a flat 2D plane, it looks a lot like a honeycomb. Each individual cell is a cluster of similar customers. The dot right in the middle is the archetype of that group.
So the exact center of one cell might represent, say, suburban moms who really like yoga.
Right. But here is the crucial mathman insight that the old madman completely missed. The most important part of the Voronoi cell isn't the center, it's the edge.
Why is the edge more important?
Think about it. The people in the dead center of the cluster are your absolute loyalists. They are already deeply embedded in that lifestyle or that brand. You do not need to spend marketing dollars on them. They are already yours. The people you want are at the boundary.
Where your cell touches a neighboring cell.
Yes. The people on the boundary are the persuadables. They're statistically very close to suburban mom, but they're also right on the edge of urban professional. They're literally on the fence.
So marketing efficiency comes from targeting the boundaries of the Voronoi cells. You want to exert just enough gravitational pull to drag those edge people into your cluster. That is a purely mathematical strategy, not a creative one.
Exactly. Okay, tool number 2, classification. This is supervised learning.
Supervised means we already know what the buckets are. We have a spam bucket and a not spam bucket, or a high-risk loan bucket and a low-risk loan bucket. We just want to sort new people into those existing categories.
And the engine powering this is usually the Bayesian classifier.
Bayesian logic is honestly beautiful once you wrap your head around it.
It really is. It's all about continuously updating your confidence level based on new evidence. It's never a strict yes or no. It's a sliding scale probability.
Let's walk through the example they give, the height and gender example.
Okay, play along. Suppose I have a database of every single adult in the United States. Millions of people. I pick one person completely at random. Is it a man or a woman?
Well, without seeing them, it's roughly 50-50.
Right. That is your prior probability, 50%. Now, I give you one piece of new data. This random person is 6 feet, 2 inches tall.
Okay, so the probability instantly shifts. Women can certainly be 6'2", but it's statistically rare. So now my confidence moves. I'm maybe 85% sure it's a man.
Exactly. You have performed a Bayesian update. Now, I give you a second piece of data. Their first name is Susan.
Whoa, okay, the probability swings wildly back the exact opposite way. Now I am 99.9% sure it's a woman, just a very tall woman named Susan.
That is exactly how the math works.
Yeah.
You take the prior probability and you multiply it by the likelihood of the new data. But there's a very dangerous trap here that humans fall into constantly. The prosecutor's fallacy.
This sounds like an episode of a legal drama.
It literally happens in courtrooms all the time. It is the profound danger of bad statistics. Imagine a crime was committed by a couple. Let's say a blonde woman with a ponytail and a black man with a beard driving a bright yellow car.
That is a very specific, unusual description.
It is. So the police search around and they find a couple that matches that exact description. They arrest them. In court, the prosecutor argues to the jury, the odds of a random couple matching this highly specific description are 1 in a million. Therefore, there's only a 1 in a million chance that these people are innocent.
To a jury, that sounds incredibly convincing.
It does, but it is dead wrong. It is a mathematical fallacy. Suppose this crime happened in a massive city like Los Angeles, which has roughly 10 million couples. If the true odds of matching that description are 1 in a million, statistics dictate that there are 10 completely different couples in LA who perfectly match that description.
Oh, wow. So if you just arrested the first couple you happen to find.
There is actually a 9 out of 10 chance, a 90% chance that you have the wrong people. The prosecutor made the mistake of focusing entirely on the rarity of the trait while completely ignoring the massive size of the background population.
That is a crucial distinction. Understanding math really can save your life, or at least keep you out of jail. Okay, let's move to the last tool. Forecasting versus prediction. I have to admit, I always thought these were just synonyms for guessing the future.
In casual conversation, sure, we use them interchangeably, but in AI and data science, they are fundamentally different concepts. Forecasting is essentially looking strictly in the rearview mirror.
Time series analysis, right?
Right. You look at a graph of your company's ice cream sales over the last 10 years, you see a clear wave pattern. Sales always go up in July, and they always crash in December. You use math, specifically Fourier analysis, to measure the exact frequency of that wave and just extend the line into the future.
So the forecast logic is, it was hot last July, so it'll probably be hot this July.
Yeah.
Buy more ice cream.
Yes. It assumes the future will be a carbon copy of the past. Prediction, however, is entirely different. Prediction uses a model of causality.
What does that mean in practice?
It takes multiple dynamic inputs. The prediction model says, if the temperature hits 90 degrees and the price of milk drops by 10%, and it happens to be a Saturday, then ice cream sales will equal X.
So forecasting projects a historical line, while prediction actually tries to simulate the mechanics of the world.
Exactly. Prediction is much harder to build, but it handles disruption way better. Imagine a massive volcano erupts and blocks out the sun all summer. The forecasting model will look at the calendar and stubbornly say, it's July, sell ice cream. The prediction model will look at its inputs and say, wait, the temperature is dropping rapidly, pivot to selling hot cocoa.
Got it. Okay, segment 5, the food. We have built the brain, we understand the language, and we have the tools. But these algorithms need to eat. And what they eat is data.
As the cliche goes, data is the new oil. And it's true. But not all oil is refined. The book highlights things like loyalty cards as an incredibly pure source of truth.
Because fundamentally, human beings lie on surveys.
We lie constantly, usually without even meaning to. This is the critical difference between active data, which is what you say, and passive data, which is what you actually do.
Right. If you stop me on the street and ask, hey, do you eat healthy? I'm going to say, absolutely, I love a good kale salad.
But your Safeway Club card database knows that you bought 3 frozen pizzas, a bag of Doritos, and a tub of Rocky Road ice cream at 10 p.m. last night.
I feel personally attacked by this data.
The algorithm doesn't judge you. It just coldly observes the truth. The authors mention a Stanford University study in the book that absolutely blew my mind regarding passive data.
Oh, the Google Street View study.
Yes. Researchers used AI to analyze millions of images taken by Google Street View cars. They didn't look at the people, they just looked at the makes and models of the cars parked in the driveways of different neighborhoods.
And they correlated that with voting records.
They did. They found that if you simply feed the AI the make, model, and year of the cars parked in a zip code, it can predict how that entire neighborhood will vote in the next election with 88% accuracy.
88%. That is vastly higher than what traditional political polling achieves.
It is. The data showed that red state voters overwhelmingly drive pickup trucks, while blue state voters overwhelmingly prefer sedans. It sounds like a broad cultural stereotype, but the hard passive data completely validated it.
And it's not just the cars in our driveways, it's what the book calls non-conscious consumption. Things like our Spotify playlists or our Netflix binge-watching habits.
Think about it. If you are consistently listening to somber piano music at 11 p.m. on a Tuesday, that tells the algorithm a massive amount about your current emotional state, your likely income level, your schedule, maybe even your relationship status. It's incredibly intimate, truthful data.
But wait a second, passive data can still be dirty, right? You have to talk about the garbage in, garbage out problem.
Absolutely.
Yeah.
You cannot just dump raw data into an algorithm. You have to clean it. And the biggest enemy of clean data is seasonality.
The famous turkey problem.
Right. Imagine you are an alien researcher analyzing Earth's food consumption data. But by sheer bad luck, you only download grocery data from the last week in November in the United States. You would logically conclude that the human race survives almost entirely on a diet of whole turkeys and canned cranberry sauce.
Which is obviously false.
So data scientists have to mathematically deseasonalize the data. You have to divide the numbers by the seasonal average to strip out the holiday spike. You want to know, is baseline turkey consumption actually trending upward year over year, or are we just looking at Thanksgiving?
And then beyond seasonality, you have the anomalies, the random spikes, the splurge.
The book makes a really smart distinction here between point anomalies and contextual anomalies. A point anomaly is weird no matter how you look at it. Like a credit card being used to buy $10,000 worth of electronics at 3 a.m. in a foreign country, when the owner usually just buys local groceries.
Right, that just screams stolen card. Yeah. Fraud detection algorithms catch that instantly.
But a contextual anomaly is much trickier for AI. Say you spend $5,000 on hotels and flights all in 1 week in July. That is a massive spending spike compared to your normal behavior. But the context is summer vacation. It's perfectly normal behavior, just in a very specific, rare context. Teaching an AI to understand context is one of the hardest parts of cleaning data.
And finally, we have dummy data. I have a confession to make here. I am definitely a data polluter.
Are you contributing to the 555-55555 problem?
I am. If I go to a website and it demands my personal phone number just to let me download a PDF report, I'm absolutely not giving it to them. I type 555-55555 and hit submit.
You and millions of other annoyed people. And because of that, somewhere deep in a corporate database, a composite profile for Mr. 55555 exists. And he looks like the most hyperactive, geographically schizophrenic shopper in the history of the world. He is simultaneously buying diapers in Ohio and expensive cigars in Florida at the exact same millisecond.
Sorry, math man. My bad.
It seriously breaks their predictive models. It creates phantom clusters in the Voronoi cells that don't actually exist in reality. Human beings are inherently lazy, and our laziness is absolute kryptonite to perfectly structured algorithms.
Okay, we have finally arrived. We understand the tech. We understand the data. Now, let's prove the thesis of the book.
Yeah.
Segment 6, the future of innovation. How do we actually use all of this to make something brand new?
Well, the very first thing we do is kill the focus group.
RIP to the sad conference room with the two-way mirror and the stale bowl of M&Ms.
Exactly. The book outlines a comprehensive 9-step process for algorithmic innovation. It essentially moves the industry from cool hunting, sending hipsters with notebooks to Brooklyn to spot what teenagers are wearing, to algorithmic extraction.
Let's actually do this. Let's play Math Man right now. I want to invent a new product. Let's say shampoo. I want to launch the next big disruptive shampoo brand. How does the AI actually help me do that?
Okay, let's walk through it. Step 1 is metaphors. We do not ask people, hey, what do you want in a shampoo? Humans don't know what they want. Instead, we have the NLP algorithms scan billions of social media posts, beauty blogs, and dermatological articles that mention hair care.
What exactly is it looking for in all that text?
It is looking for the underlying meaning behind the product. It's analyzing those vector spaces we talked about earlier. It might find that the vector for shampoo has drifted away from the vector for cleaning. Soap is for cleaning. Shampoo has moved closer to vectors like self-care, ritual, and confidence.
Okay, so the AI is telling us, we aren't selling clean hair anymore. We are selling my time or empowerment.
Exactly. Step 2 is trend sorting. The AI identifies thousands of different product attributes from the text, scents like lavender, ingredients like argan oil, packaging concepts like minimalist glass. It sorts all these attributes into 3 distinct buckets: dominant, fading, and emerging.
Dominant means everyone already does it. It's boring. Fading means it's yesterday's news. Emerging is the cool stuff on the horizon.
Right. So if the ingredient-activated charcoal is in the fading bucket, the AI explicitly warns us, do not launch a charcoal shampoo. You missed that wave.
Okay, so what is step 3?
Concept generation. And this is where the math gets wild. The AI takes the emerging trends, maybe CBD oil and yuzu scent, and combines them with the self-care metaphor. It mathematically generates millions of virtual product concepts overnight.
Like a CBD-infused shampoo bar with biodegradable packaging that smells like yuzu citrus?
Exactly. Or a probiotic scalp treatment that comes in a refillable glass jar. It iterates every possible logical combination of the emerging attributes.
And then what? We can't manufacture a million different shampoos.
We don't. Step 4 is virtual testing. We don't mix a single chemical. We test these million concepts against the consumer data models we built back in segment 4. We present the digital concepts to our digital Voronoi cells. We basically ask the algorithm, would this specific cluster of people buy this specific combination?
We run a massive simulated product launch.
Yes. And the model spits back the results. It says, the CBD bar will flop completely with suburban moms, but the probiotic scalp treatment will be a massive viral hit with urban millennials on the boundaries of these 3 clusters.
So we have successfully narrowed a million completely random ideas down to the mathematically proven winner, and we did it without renting a lab, mixing a batch, or filming a single expensive TV commercial.
That is what innovation at the speed of light looks like. It's finding the needle in the haystack by virtually burning down the haystack and running a giant electromagnet over the ashes.
That is just incredibly powerful. It completely changes the role of the marketer. You go from being a guesser to being a guide for the algorithm.
It really does shift the entire paradigm of product development.
Well, we have covered a massive amount of ground today, from the synapses in our brains to the aisles of the supermarket. Let's bring it all home with the outro. What is the one big lingering thought you want the listener to take away from this deep dive?
I want to circle back to a quote from the book that really stuck with me long after I finished it. The authors write, AI is almost a humanities discipline.
Which honestly sounds completely counterintuitive after we've spent the last hour talking about mathematical vectors, isolated circuits, and von Neumann bottlenecks.
It does sound strange, but think about it deeply. To build a machine that can effectively sell to us, or help us, or talk to us naturally, we have to quantify what it actually means to be human. We have to write hard code that defines slippery concepts like intuition. We have to map out vectors for abstract feelings like love and comfort and nostalgia.
So in obsessively studying and building the machine, we are really just studying ourselves in a digital mirror.
Exactly. We're trying to reverse engineer the human soul just so we can replicate a fraction of it in silicon.
That is beautifully put, and also, I have to admit, slightly haunting.
Well, if you like haunting, let me leave you with one final provocation. The authors briefly touch upon the philosophical idea of superintelligence.
Oh boy. Lay it on me.
We humans deeply value our consciousness, that little voice running inside your head, the I that is you. We naturally assume that consciousness is the absolute pinnacle of intelligence. But functionally, consciousness is actually very slow. It acts like a spotlight. You can only shine it on one thing at a time. You cannot read a complex book and drive a car through traffic and solve a math equation simultaneously.
Right, that's the biological bottleneck we talked about.
Exactly. But an artificial superintelligence, it processes vast global databases simultaneously. It doesn't have a narrow spotlight. It has a floodlight that illuminates everything at once. So the terrifying question is consciousness actually outdated?
Wait, is the I, the sense of self, just a legacy biological feature?
Is it merely a biological bug that a truly superior intelligence simply won't even need? We assume machines will eventually wake up and become conscious, but maybe the future of intelligence isn't more conscious. Maybe it is entirely devoid of consciousness, yet infinitely more capable.
That is a thought that is going to keep me staring at the ceiling tonight. I'm going to be laying in bed wondering if my entire sense of self is just obsolete software.
Well, ideally, you'll be wondering if the ceiling fan above you was designed by a genetic algorithm.
Touché. Well, on that deeply existential note, that is a wrap on today's deep dive. Next time you open up Netflix or Amazon and you see that curated list of recommended for you, don't just mindlessly scroll past it. Take 1 second to realize what you're looking at. That is not magic. That is a Voronoi cell suspended in a high-dimensional vector space, actively trying to understand who you are better than you understand yourself.
And statistically speaking, it's probably succeeding.
That is a fascinating perspective to leave off on. Thanks for listening, everyone. We will catch you on the next deep dive.